All right, so this video is going to be the NMSI packet for circular motion, gravity, and orbits multiple choice answers. So let's go ahead and get started here. Number one says 4 satellites are in a circular orbit about the Earth, well outside the atmosphere. The mass, m, and orbital radius r of each satellite are given below. Which satellite has the greatest speed? So what we're going to do here is we need to calculate or get an equation for speed so we can kind of look at this. And knowing that the only force that's responsible for the centripetal force here is going to be gravity. So if I have my equation that looks like this, oh, sorry, right? I know the only force that's responsible for that is gravitational force. So I have G, I'll have mass satellite, mass Earth, I have radius squared equals mass satellite, sorry, velocity squared over r. Okay. So then what we kind of want to do here is we want to get an equation that says v equals. So then we can see how changing the variables is going to change the velocity here. So I'm going to, the mass of the satellites actually cancel out. And if I bring the r over there, I get I get an r up top, so that's going to cancel out and cancel out one of those. So I get mass of the Earth divided by r equals v squared. I'm just going to square root both sides, so I get v equals the square root of big G mass of the Earth over the radius. All right, so this is the equation for the velocity of the satellite. Now, let's look at the changes we're going to make to see which satellite has the greatest speed. Okay. So the first one, satellite A, should make sense that it's not going to be any good because you're making the mass smaller. So if I put a smaller number up top inside the radical, I'm going to get a smaller number out, which makes it a smaller velocity. Okay, so A right away, no good. So next, you notice B, C, and D have the same mass. Okay, so now there's no difference there. So let's see what's happening to the radius. So to get the biggest velocity, we would want the smallest number in for r, right? Because if you're dividing by r, if you divide by a smaller number, you're going to get a bigger number in result. So if I look here, the radiuses are r divided by 2, you got r, and you got 2r. So the smallest one there would be r divided by 2. So therefore, that's going to give me b. So the answer here is b would give you the uh, highest velocity. Okay. All right. Going on to number 2. Number 2 is kind of a long one here. So, and you gotta remember some stuff that before it goes. That's density equals mass divided by volume. All right. So it says 2 spherical planets have radii r1 and r2 such that r2 equals 2r1 and the mean densities of p1, rho 1 and rho 2 respectively. The accelerations of gravity a1 and a2 of the planets are related by which of the following? All right, so we need to get an equation that says the acceleration of planet 1 equals this. Well, if you remember, our acceleration due to gravity equation was this. Okay. So instead of calling it little g, because that's what we do on Earth, we'll just call it a. So let me erase this because we're going to use this equation a little bit later. So that's a. That's going to be the acceleration due to gravity. So again, what we got to kind of look at here is, we know the densities, and what we're going to do is compare the densities, make an equation where it has the densities involved with it. So what we need to do is, as you can see, there's no equation or no density in that equation. So what we got to do is kind of get it in there. Now, the only variable that connects this, remember, this is volume, not velocity so that's volume. Okay, volume for a sphere right? There's our equation for volume of a sphere. And again, you could have looked these up. And if they ever do this on an exam, they would give you this information, or it's on your equation sheet. So what I want to do is I want to get this equation to say mass equals, so I can plug it into the acceleration equation here. So I'm going to get mass equals uh, rho volume. And then if I plug that in, I'm going to get mass equals 4/3 pi r cubed times rho. So I know that is what my mass of each sphere equals. Okay. So, when I'm plugging this in for this, so if that's my mass, all right, let's just plug in just basically for one thing here and kind of look at what it boils down to. So I'm trying to find acceleration. I know big G is just a number, and I'm going to plug m in here, right? So I got 4/3. I'm going to leave r squared at the bottom. Pi r cubed times rho. Okay. All I did was plug in there to this equation. So if I look at this, okay, G is a constant value. So regardless if this acceleration was for planet 1 or planet 2, G is the same. 4/3 is the same. Pi is the same. So all of those are constant values here. So if I look at this, G, 4/3 pi, these are all constants. So effectively, I can cancel those out because it's going to be the same for, like, those are going to be involved in each equation for A1 and A2, okay? So if I look what I'm left with, I got cubed on top and squared for the radius on bottom. So this cancels out, and I'm left with just R and rho. So I know the acceleration basically comes down to the radius of the planet and the density. All right. So now if I want to look at these, so I'm going to compare these. So I'm going to compare like a little ratio here. So I'm going to say A1 and the ratio A2, they're equal to. So let's look at what A1 would be equal to. A1 would be equal to radius 1 times the density of 1. A2 would be equal to radius of 2, density of 2. Okay. Now, what we have to do is keep going here. I know that from this thing right here, that R2 equals R1. So what I can do is plug in even more. So I can go A1, A2 equals R1, rho 1. And I go R2 is equal to 2 R1, rho 2. Okay? So what I get here is I end up getting the R's to cancel out, okay? And I'm left with A1, A2 equals rho 1, rho 2 with a 2 down there. So like I said, you need to get the equation to say A1 equals, I just multiply by A2, right? Multiply by A2, multiply by A2. So you should get A1 equals rho 1 A2 over 2 rho 2. Let's see, is that B? A2, yep. Rho 1, 2, rho 2. Good. So your answer here is B. All right. Let's keep going here. So it says, two objects are separated by distance r if the gravitational force on the two is decreased by 1/3 its original magnitude without changing either mass. The mass have to stay the same. Then the separation distance must become, okay. So this is looking at force. So we're going to look at this equation here. The only thing we can change is the radius, and we need it to go, has to become 1/3 f. So how could we change this? Well, it should make sense. We're changing radius because we can't change these two. It says mass stays the same. So basically, what we need to come out is we need to get a 3 down here. Okay. If we get a 3 down here, it's divided by 3, which is in fact basically this. So to get a 3, since it's squared, I would have to do this. If I did the square root of 3r squared, what happens is that ends up canceling out. So I'm going to get 3r squared, squared, and that gives me my 3 on the bottom. Okay. So what answer is that? That is C. C is your correct answer there. All right. 4. Two sacks contain the same number of identical apples and are separated by a distance r. Exert a gravitational force on each with a magnitude F. Half the apples in one bag are placed in the second. What is the magnitude of the... Okay, so we're looking at force again, so let's write the equation out. So the R stays the same this time. So that's staying the same. Now what's happening is, so if I have M1 and M2, right? It's saying that half of the apples, so I'm getting half of M1 is now going to M2. So I'm going to basically give the half over here. So this ends up being 3 halves. So here's our new masses, right? The original one that you take half the apples out is half of the mass. And the new one is 3 halves of mass. So if I now plug in to see what my ratio would be, so I go F, big G, I got 1/2 M1, and I got 3 halves M2 over R squared. If I do multiplication here, I got 3/4 is my factor, right? 1 times 3 is 3. So I got 3, 2 times 2 is 4, M1, M2 over R squared times G. So my factor here is 3/4. So therefore my answer would be B. All right. Number 5, a satellite mass 3,400 kilograms is in circular orbit around a planet of radius 9.4 times 10 to the 11th meters from the planet's center. If the speed of the satellite is 20.5, what is the gravitational force acting on the satellite? All right. So same thing like we did before. We know that gravity, so if I got my centripetal force equals MAC, I know gravity is my one here. So I go big G, M satellite, M planet over R squared equals mass satellite V squared over R, right? So again, satellites cancel out. This cancels out one of those. So I get velocity equals the square root, or no, what am I trying to solve for? Oh, the force. Oh, I'm looking for the force. My bad. So I did too much here. Sorry, I did too much. FC equals M V squared over R. Sorry, I was going way into it. It's very easy here. You can just plug and chug. Mass of the planet. No, I'm sorry. That's mass of the satellite. 3400. Velocity is 20.5 squared over R, which is 9.4 times 10 to the 11th. So you do that in your calculator. What do I get? 1.5 -6 newtons. Yeah. So the answer there is going to be B. 6, a coin of mass M is placed on a vinyl stereo record of radius R and moves at a constant tangential speed V. If the frictional force between the coin and the vinyl record is at maximum value, then which of the following expressions can be used to find the value of the coefficient of friction between the coin and the vinyl record? Okay, so what we have to think is, what is causing the centripetal acceleration or the centripetal force? Well, in this case, what's holding the coin on the record would be the friction between the coin and the record, right? So when I write this equation, when I say centripetal force equals mv squared over r, I know the centripetal force, this is equal to friction. Well, I have an equation for friction. It's mu Fn. So if I go mu Fn equals mv squared over r, okay? Now, let's think about the free body diagram here. Here's the coin on the thing. I got weight going down, mg, and I got normal force going up. I know it's not moving up or down, so I can say that my normal force here is going to equal the weight in this case. So I'm going to plug in from that. I go mu mg equals mv squared over r. So I want to solve for what? I want to solve for mu. So I'm going to divide the masses cancel out. So I get mu equals v squared gr. Is that right? Let's see what I get. 6 should be d v squared gr. Yep, there it is. Okay. And this just goes to show like the centripetal force could be anything. Whatever the force is that's keeping the object in the circular path is the centripetal force. In this case, it was the friction. Okay. All right, next one. An object that revolves in a uniform circular motion, which of the graph best represents the centripetal force on the vertical axis? So on the y, and the speed on the horizontal axis, right? So if I look at my equation, all right, if these are my two variables I'm looking at, that's going to be squared, right? So what should I expect? So my answer there is C. All right, pretty straightforward. That one's pretty easy. Eight. Okay. A child sits on the edge of a merry-go-round, radius 6 meters. The tangential speed of the child is 12 meters per second. Oh, okay. Yeah. We're not going to do this one. I'm going to do it just so I have this and it's complete, but you don't need to know this for, the class. The work done by the centripetal force during one revolution is this. So if we look at our work equation, work is equal to force times distance times cosine of theta. All right. And work is also equal to change in kinetic energy. Now, here's the problem here. The centripetal force here, the angle between the force and the displacement is going to be 0 degrees, which then cancels this out to be 0. It gives me the work to equal 0. So the work here is equal to 0. Therefore, the kinetic energy is equal to 0. Okay. So therefore, my answer is going to be A. Number 9. So you need this picture. So just remember 1 is up there, 2 and 3. It says a ball at the end of the string is being swung in a vertical circle rotating clockwise as shown above. Which of the following vectors represent the centripetal force acting on the ball at position 1? So you need the centripetal force acting at position 1. That's pretty easy. Which way is it always pointing? It's pointing to the center. So my answer there is going to be D, right? It's pointing to the center at 1. So therefore, pretty easy. And what's it give me? 10. If the string were suddenly cut when the ball is at position 2, shown in the figure, the subsequent motion of the ball would be, all right, so we're looking at part 2. Okay, so remember here that the velocity vector is always tangent to the circle, right? We always draw a tangent. So if that string would be cut there, the ball would move up and down, right? Or I don't know what the answers are or the options are. So let's just go look at the options. It says move to the right, no, move to the top of the page, right? Because it's going to go up. So therefore, the answer there is going to be C. All right, so number 10 is C. Number 11, the tension in the string is. So when we think about the three positions, okay, um, at the top, think about it. There's tension and weight pulling down. At the bottom, okay, there's weight pulling down and tension pulling directly up. And over here, you have weight pulling down and then tension pulling horizontally, okay? So the point that's going to have the most tension in the string is whenever it has to go directly against the weight, all right, which is when it's at the bottom. It has to go against, the centripetal acceleration required to go around, and it has to go against the weight. So therefore, I know that at position 3, it's going to have the greatest amount of tension. So let's read this as greater at position 1 than position 3. No, that's opposite. Greatest at position 2. No, greater at position 3 than position 1. Well, that's true. And greater at position 1, no. So your answer here by process of elimination and knowing that position 3 is greater is going to be C. If I could get it to right. All right, so because 3 is the greatest. The ball has a mass m and a speed v as it moves about the circle and a radius r. Which of the following expressions can be used to find the minimum speed of the ball at position 1? So what we need to do here is draw a free body diagram. So if we're at position 1, I know the tension and weight is going down. All right, so if I do this, now, the key to this is the minimum speed, okay? The weight's not going away. You can't get rid of weight, okay? So to get the minimum speed, we would want the minimum amount of centripetal force. The minimum amount of centripetal force we could get there is just having the weight be the centripetal force, right? Because if I would speed up from the minimum, then I would need some tension to bring it down. Does that make sense? To curve it into the circle, okay? The faster I go, the more tension there is. But there's always going to be weight pulling down, okay? So when looking at this, that means to find the minimum speed here, my tension is going to be 0. So if I look at that, I'm going to have my weight, I'm going to have times mass, v squared over r. So if I solve that for v, what do I do here? These masses cancel out. I get square root of gr equals v. Letter A. So your answer. Okay. All right. I think that's it, right? It's only 12. There's only 12. Yep, that's it. So that concludes it for this video.